So here are two assumptions. We'll start with two very, very basic assumptions, which I think are not very controversial. One is that a software system embeds a representation of reality according to a particular worldview. So every software system embeds a kind of information structure that has real world semantics, that represents a certain portion of reality. And this is true even if we're dealing with software systems which are very data driven and in which you have very generic algorithms, right? So let's say what people call these days AI systems. Even in this case, I like very much this quote here by Timothy Hannigan, that it's not heaps of transactional data that makes an inquirer scientific, but being scientific is an effect of work done to establish stable, quantifiable concepts. The concepts are a prerequisite for the existence of data. So even if you have something that seems not to have a explicit representation of a certain portion of reality, you have to do this kind of conceptual work to separate signal from noise in the data. And also, if you think about it, people that concentrate these days on data-driven applications and try to dispense with domain modeling and say, we don't need domain modeling, we just need, heaps of data. They don't realize that when they have to spend 80% of their time doing data cleaning, they are doing conceptual modeling in another sense, right? So it's by looking at a conceptual model or a domain model that you realize that you can judge the quality of data and you can fix problems in the data, right? So that we are just transferring the problem elsewhere. Doing data cleaning and doing data preparation in the end requires sometimes not explicit, but requires a kind of conceptual model or domain model, some sort of structure that represents a domain from a particular perspective, a worldview from a particular perspective. So this is the one slide I'll talk about this. And that, again, the assumption here is this one. Every software system embeds a representation of reality according to a particular worldview. So in other words, every system commits to a given theory of what exists, what it takes to exist in a given domain reality, right? So even if you take the most mundane software system, a database like this database or this system believes in the existence of things like, people that could be living or deceased, transplants, surgeons, donors, donees, and so on. So this system believes these things exist, that they have certain relations between them, that they have certain properties, and that they obey certain domain rules. In other words, this system necessarily makes an ontological commitment. It commits to a particular worldview, right? And this is something that is very, very well known in conceptual modeling, computer science in general. Actually, the first appearance of the term ontology in computer science refers to this sense of the word ontology. Ontology as a method of analysis that allow us to articulate what kind of commitments, ontological commitments, are being made by a certain information structure. The first appearance of the word ontology in computer science is in this paper called Another Look at Data by George Milley. George Milley is the creator of Milley automata in computer science. He's also the PhD supervisor of Peter Chang, who later created ER diagrams, right? So he's the grandfather of conceptual modeling, let's say, of domain modeling. So in this paper, George Milley defends that data are fragments of a theory of the real world, and that data processing juggles representation of these fragments of theory. This issue is one of ontology or the question of what exists. What is the commitment, right? And I'm saying this, this is exactly the intention behind this statement. When referring to ontology, Milley actually refers to a philosopher called Willem van Orman Quine, on a paper called What There Is, if I'm not mistaken. And Quine had this view of ontologies as that the ontology of a representation or of a language or of a grammar and so on is what that representation structure has to assume to exist in order for it to function, right? What kind of entities you must assume to exist in order to give a particular description of reality. This is the view of ontology put forth by Quine, and this is the idea defended by Milley here, right? That in order to build any kind of information structure, we need it's an issue of ontology. We need to articulate what are the elements of this worldview. So this is from 1967. It's so much earlier, 10 years earlier than what people believe is the first mention to the word ontology, which is the paper by Pat Hayes called the Naive Physics Manifesto in the end of the 70s, which refers to ontology in a different sense. We'll come back to this. This is true even, in programming, right? Even if you're not consciously thinking about domain modeling at all. I very much like this quote by Donald Knuth, right? Who wrote the Turing Award winner, who wrote the science of computer programming, in which Knuth says programming is about telling another human what you want the computer to do. So it's not about telling the computer what you want the computer to do at all, right? If that were the objective, you would talk to the computer in a completely different way. Programming is about communication between people, right? Of what you want the computer to do. So again, anything that has any information structure which has some real world semantics, which is not just a piece of mathematics, will make an ontological commitment. So this is the first takeaway message. In designing systems, designing information systems, software systems, the opposite of ontology is not non-ontologist, bad ontology, because you're going to do it anyway. Every time you create a class diagram, every time you create a database, every time you give some real-world semantics to your variables in a program, and when you are deciding, telling apart signal from noise in heaps of data, you are doing ontology work anyway, sometimes without the proper tools. There is another sense of the term ontology, which is ontology as a particular theory, right? Not as a method of analysis, as analyzing and articulating the things which exist in a particular domain, but as a theory about the kinds of entities and their ties that are assumed to exist by a given description of reality. So in that sense, articulating that worldview, which is embedded in the information structure of a computer system, is defining a ontology with lowercase o now, right? And that's the sense referred to by Pat Hayes in this Naive Physics Manifesto. So in that sense, what I'm defending here is that the domain model is a kind of ontology in this sense, right? Because you're deciding, if you're doing, I'm not talking about design models or implementation models, but the conceptual model that will give rise to the thing that will end up in your application is developing a particular domain ontology. And again, we should do this. It's not always a good ontology, and we should understand the tools which are available out there in order to develop this ontology as a good ontology. So one fundamental attribute of an information system or of a software system is what's called domain appropriateness, right? So you want to guarantee that the information structure embedded in your system is truthful to the domain being represented, right? Obviously, you are considering a certain perspective, a certain granularity, which is useful for a particular class of applications, but the model itself should be truthful to that conceptualization, that particular conceptualization of the domain. In two obvious sense, in the sense that it should be able to express the relevant distinctions in the domain, the relevant ontological distinctions, and that this information structure should be constrained in a way that the only possible interpretations of this thing are the intended ones, right? So let's make an example. Imagine if you're doing a very, again, I'm thinking about a very mundane system like the one we just saw, in which you're talking about transplants and so on. Obviously, in reality, you cannot be living and deceased at the same time, right? And once you've been dead, you cannot come back to life, right? So these are rules which are rules of the domain itself, rules which are given, which are part of the domain of these distinctions and the meaning of all these distinctions. And this should be reflected in your information structures in your software system, right? So a system in which people can come back from the dead, or the people who are living and deceased at the same time. This is a system that has a possible state, if you like, a valid instance of that information structure, which is not intended, right? So these are the two obvious sense in which doing this model right, doing this conceptual model right, contributes to this very important quality property of a software system, which is domain appropriateness. The system should represent in a clear way, in an unambiguous way, the relevant domain distinctions, and the system should only allow states, populations, instances, right? So if you think about the model and an instantiation of this model, the possible instance of that structure should be instances that are admissible by the rules of the domain in reality. Now, a second assumption, which I think it's also very uncontroversial, right? That modern software systems, so everything that I said so far gets more critical, more complex, because all modern software systems are built in a collective and distributed manner, right? So basically all systems that we create, especially in critical domains, right? So finance, security, healthcare, and so on, you're gonna build the systems by reusing things which already exist, by putting together systems which were developed in an autonomous concurrent way. And everything you develop will eventually be integrated with other things, right? Everything is development for and with reuse. And the question and the reason for that is that basically all important questions we need to answer in science and in government and in organizations can only be answered if we put together data which now reside in concurrently developed, autonomously developed data silos, right? So just to give one example, imagine if you're in the government and you want to know all companies that have a contract with a governmental unit, a governmental organizational unit, that donate money to the political campaign of everyone who could have influenced the establishment of that contract, right? I mean, in order to do that, in basically all governments I know of, you know, this question could be answered because this information is there. It's in the ether, is often actually public. But in order to answer this question, you have to put together 4 or 5 different information systems, right? One about outsourcing contracts, one about the structure of government, so how the governmental entities are decomposed, one about people's allocation and hierarchy in this different structure, one about political campaigns and donations and so on. So these things all exist out there, but in order to answer this question, you have to integrate these things, right? And in fact, I mean, if we look again, if you look at big data, we, you know, people often put these 4 V's in the same footing, right? But if you look into the details, it's clear that they are not, right? The real problem with big data is not variety or volume or velocity. Sorry, it's not volume, velocity, and so on. The real problem is variety, right? It's the heterogeneity of data and the distribution of data, and how to put these things together in a consistent and safe manner. So again, the problem that we just saw, so this idea that your system should have domain appropriateness, now your system should maintain the system of systems, so the system which integrates several pre-existing systems has to maintain these properties, right? Has to be such that the collection or the network, the federation of information structures which are embedded in all the systems will be a consistent, a truthful representation of that portion of reality, and would only allow for states, for valid states or population or instance, which are intended, right? This is particularly serious in some domains because the facts, the information facts in this collection, in this collective database, or in this collective information structure, this integrated information structure, is what grounds institutional facts in reality, right? So for example, take money. If money becomes just information records in some software system, the grounding of the institutional fact that you're entitled to a certain amount is a state of this database, right? Or a state of this integrated information structure. And so is that you are that you become a person of interest, or that you own a certain property, a real estate, or that you're married with someone, or that you own taxes to the government. I mean, these are all the brute facts which ground institutional facts in this kind of digital reality is these are sets of integrated digital pieces, items of information, right? Then, so the issue here is that when we want to put these systems together, when we want to interoperate make these systems interoperable, and we need to put together the different worldviews, the different ontologies, which are embedded in these different systems, right? So the problem of semantic interoperability, it's actually very straightforward to define. It's finding out how these pieces of information which reside in these different silos are connected, how they relate to each other, how to relate the worldview which is embedded in a particular system with the worldview which is embedded in another system. So if we look at these two systems, so semantic interoperability is relating different worldviews or relating different conceptualizations of reality, right? So in order to understand, for example, what is the relation between person on the left and person on the right, I have to understand the relation between their reference, so the elements in reality that they represent, right? And what is the relation between person on the left and person on the right? Or what is the relation between transplant on the left and transplant on the right? Can we assume is a relation of identity just because I'm using the same lexical term in both cases? And if not one of identity, what then? What are the other possible relations between these things? Maybe specialization, maybe composition, maybe dependence, and then what kind of dependence? Existential dependence, generic dependence, historical dependence, and so on, right? So for example, existential dependence is the relation my headache bears to me, in a sense, right? So my headache can only exist if I exist. The marriage between John and Mary can only exist if John and Mary exist. This is existential dependence. Generic dependence is, in order for someone to be a parent, they need to have an offspring, right? In order for someone to be an employee, they need to have an employer, but it doesn't have to be the same employer, right? That's why it's called generic dependence. Historical dependence is a specific dependence, but not existential dependence. Like I'm historically dependent on my parents, but I don't need to exist at the same time they exist. They just need to have existed before I exist, right? So I'm talking about three different types of dependence. And there are many other possibilities for relations between these things. So we need a kind of toolbox, right? We need a vocabulary and we need a toolbox to calculate the meaning of these different information items and to figure out exactly what is the relation between them, right? Because once I figure out what kind of relation, then I can axiomatize, for example, this relation in the way it's implemented in the information system, right? And I'm saying axiomatize not only, if you're doing declarative logic-based systems, even if you're implementing things, you have somehow to implement the semantics, right? So for example, if we know this is an identity relation, we know that an identity relation is reflexive, symmetric, and transitive, so an equivalence relation, but it also obeys what is called Leibniz law. So if two things are the same, they have the same properties necessarily, right? So if I know A is identical to B, everything I know about A, I know about B, and everything I know about B, I know about C, and everything I know about A, then I know about C. That's why if it's not one relation of identity, assuming its identity is dangerous because you propagate these properties in an uncontrolled way, right? So before we go writing formulae and axioms and constraints on how these things should be integrated, we need to figure out what is the relation that can be established between these elements represented in information systems, in different software systems, even if we use the same lexical terms to refer to them. Right? So again, this area devoted to developing these domain-independent toolboxes, theories, and methods for doing this kind of analysis is the area of ontology for 2,400 years. So it's a good idea that we leverage on that and we don't try to reinvent the wheel because we don't have 2,400 years, so we're going to end up creating a squared wheel, right? So ontology with capital O, sometimes it's what's called formal ontology in philosophy, is this area that would put forth a number of theories of what is dependence, what is identity, what are the sound taxonomic structures that can be formed, what are relationships, what are events, what is causality, what is parthood, and so on, right? So the theory, this area produces this kind of theories. That's why it's actually called formal ontology, not because it's mathematical. That's another common misconception that people have of the term formal ontology, that formal ontology means it's written in logics, but it's actually formal in that sense, in the original sense, means domain independent. So it's related to form and not to content, right? And mathematics is formal because it's domain independent. So if you know that 3 + 5 is 8, you don't care if you're talking about apples or oranges or cars or people, right? So it's independent of content. And if you understand identity or parthood or causality, and so on, you can take this domain-independent knowledge and structures, and as we'll see, patterns, and reuse them in many different domains, right? So this is the normal thing in mathematics, in logics as well. So logics is, in a sense, neutral with respect to truth. You use logics just to derive, to do sound reasoning, in a sense, so to derive information from explicitly defined information. So if you have that A and not B, then C, you don't care what A and not B mean, right? You don't even commit if A and B are true or not. You're just saying if A is true and B is not true, then C is true, for example, right? Ontology, formal ontology in that sense, is neutral with respect to reality. So, for example, I don't know if Renata has a headache, but Renata's headache can only exist if she exists, right? So it's this kind of calculus of consistent within a set of conceptualization choices. So what I call intra-worldview consistency. You have to guarantee that the set of choices you make within a conceptualization and within a model are consistent among themselves. And you have to do this in a very explicit way, such that you can safely connect different worldviews. So intra-worldview consistency and inter-worldview interoperability, right? So ontology is this area that will give you tools for doing that. Now, again, this is an area that exists in philosophy in one way or another for more than 2 millennia. It was established as a kind of independent discipline by Edmund Husserl in the 200 years ago, let's say, bit less than that. And what happens for us that we are engineers, we need to have an engineering discipline for building these particular representations of particular worldviews that we want to embed in our systems, right? So what is called ontology-driven conceptual modeling is this engineering discipline for building ontology-driven conceptual models or domain ontologies. And what is an ontology-driven conceptual model or a domain ontology? That thing that you want to create in order to derive requirements and design your software system is a model representing the result of ontological analysis over a given domain. An analysis conducted with the theories and tools put forth by this area of ontology, right? So I think this is an important, maybe this is the second takeaway message, that what makes something an ontology is not the language that you use to represent it. And because this is the most common misconception that you see these days, that people use a particular type of logics, which has nothing of ontology in it, the ontology web language, for example, OWL, and we say that that's a sufficient and necessary condition for something to be an ontology. You can create ontologies in first-order logics, in OWL, in UML, in ER diagrams, in natural language, if you want, right? In Haskell. The ontology is not, being an ontology is not something which defined by the language you use to create that artifact, but the method you use to create an artifact. That is meant to be a representation of the result of analyzing the domain using ontology-based techniques with the capital O, right? It's the result of it's the representation of the result of an ontological analysis. Now, the language you use, and now let's just mention a little bit this criteria for the quality of language, right? The language you use can be better or more suitable or not for doing that. So how can I judge if it is better to use OWL or Java or Haskell or UML or ER diagrams or first order logic or something else? Well, think about it for a second. I mean, how do you judge the suitability of a language to represent any type of phenomenon in reality, right? We go back to that discussion about domain appropriateness. So imagine if I'm designing a language to represent genealogical relations. What would be an ideal language for that? Well, it's a language that has modeling primitives which reflect the relevant domain distinctions, domain appropriateness. So I should be able to represent father and mother and ancestor and this descendant and offspring and so on, right? If a language doesn't allow me to do that, this would be a language that lacks expressivity. The language should also be unambiguous in the sense that when I look at the primitive of the language, I should unambiguously interpret that in terms of a domain notion, right? So a language that uses the same symbol to represent ambiguously father and mother would be a poorer language. Third, the language should be such that it should not allow me to build models which conflict with the domain rules. So a language to represent genealogy that allows me to be my own father or to be an ancestor of mine, or to allow me to have two biological fathers or have a biological father that changes in time. This would be a poor language in that respect, right? So by looking at this aspect of this mapping, this kind of isomorphic relation between what there is in the domain and what the language is able to talk about and how, we can judge the quality of a language to model phenomena in a given domain. The same holds here. How do I know if first order logics is it's adequate for representing ontologies in the sense that I just proposed? Well, let's look at what are the primitives of first order logics and what are the notions, the concepts, the meta concepts that I use to conduct ontological analysis. I mentioned that we need to talk about identity and we need to talk about the different types of dependence and parthood and so on. Are these things reflected in the primitives of first order logics? No. Are these things reflected in the primitives of OWL? No. Are these things reflected in UML? Not really, although you have the notion of type and specialization and some sort of theory of parthood embedded in these notions of composition and aggregation, a very poor theory, by the way. It's not really adequate, right? So if I look at the ontology behind UML and the notions that I use to do this kind of ontological analysis, there is a huge distance between these things, right? So an ideal language to build ontologies as domain models, which represent the result of an ontological analysis, is a language whose modeling primitives reflect exactly those elements in my toolbox that I use to do ontological analysis, and a language which syntactical constraints, grammatical constraints reflect the general axioms of the elements in that toolbox, right? So a language that would not allow me to build models that would conflict with these ontological notions. This is an important point, and we will come back to this, to the characteristics of a particular language that was designed to do exactly that. So I'll mention now about a particular set of results, very concrete engineering results that follow the path that I just mentioned, that I'm advocating here, right? So we start with what is called a foundational ontology or a foundational theory, which is a particular system of domain-independent formal theories about all these things that you need in order to do domain analysis, right? You need to understand classification and taxonomic structures and parthood and multi-level modeling, so having types which are instance of other types, you need to understand dependence, you need to understand different types of relations and relationships, events, roles, and so on. So in a sense, this ontology and this particular foundational ontology, set of foundational theories, let's say, called UFO, the Unified Foundational Ontology, has been developed for the past more than 20 years with the goal of developing foundations for all domain modeling constructs, all conceptual modeling constructs. So it has a theory of parthood, it has a theory of dependence, it has a theory of events, and a theory of how to build taxonomic structures and so on. Now, from this, we have, again, for the past 20 years, been developing a set of engineering tools based on these foundational theories. In particular, a modeling language, and much of our focus here will be on one particular modeling language, conceptual modeling, domain modeling language, which has the characteristics that I just mentioned. This is a language called OntoUML. It's basically a redesigned version of UML class diagrams. I can comment why, extending UML. The idea there is that you extend the UML metamodel such that the metamodel will include distinctions for the ontological distinctions put forth by those foundational theories, and the grammar in the metamodel will include semantically motivated syntactical constraints that reflect the axiomatization of those foundational theories. If something does not make sense from the point of view of those foundational theories, it will show up as a syntactical constraint in OntoUML. So there are things you cannot do in OntoUML. UML would allow you to do anything. First order logics would allow you to do anything. It's completely unconstrained, exactly because it's ontologically neutral, right? OntoUML, on the other hand, will constrain how these primitives can be connected, reflecting these ontological rules, right? This is analogous to what I said about genealogy, right? You want a language that constrains you in the right way, wouldn't allow you to be your own father, for example, or to be born before your parents or something like that, right? So beyond this and this modeling language, we have developed, methodologies, computational tools, patterns, anti-patterns, code generators, simulators for validation, for model validation, many different tools for complexity management, and even an approach for constraint learning that I'll mention later in the talk. Now, once we have these tools, this ecosystem of tools, we can use them to build domain-specific theories. And that's, again, what we have been doing for a long time in different domains, also to test all these different tools, right? So, for example, we did quite some work in building domain ontologies or domain models in different domains in software engineering, like, for example, software configuration management, software adaptation and runtime evolution, software defects and anomalies, function and non-functional requirements, and so on. In fact, if people are interested, we have an entire network of ontology models, connected ontology models, which is available, right? In this different subdomains of software engineering. It's called SEON, Software Engineering Ontology Network. We also did quite some work on economics, microeconomics, and finance. So, for example, on service and value and economic transactions, trust, contracts, preference, money, risk, ethicality, trustworthiness, and so on. And one of these, let's say, domains is that Renata will use later in the talk to illustrate how this can be used then to derive requirements for specific systems.